Viewers like you make this program possible. Support your local PBS station.
$700 million years ago, ice threatened to make our planet uninhabitable, snuffing out new complex life forms.
This is some of the deepest, most intense cold that Earth has ever experienced.
Some people think the planet was completely encased in ice, a so-called snowball Earth.
You would have seen it as a glistening white marble hanging in the blackness of space.
A seemingly impossible fate for a planet so close to the sun.
When snowball Earth was first proposed, people thought it was an outrageous idea that this actually could have happened on Earth.
But now, new techniques that are peering into the past say it was not only likely,
now we have geological evidence that nearly the whole world was plunged into a deep glaciation.
but also lucky for us.
This snowball event most certainly shaped life on Earth.
From this climate catastrophe, new forms of life arose, eventually leading to the living world today. But it was a close call. How did life survive in this planetary deep freeze and thrive in its aftermath? Ancient Earth, frozen right now on Nova. Nearly 1 billion years ago, most of Earth's land forms a single giant continent. Rodinia. Thousands of miles coast to coast, this enormous landmass dominates the planet. But despite its size, from its jagged peaks across its desolate lowlands, there are no plants and no animals. Yet, in the shallow coastal waters, there is life. Microscopic bacteria gather to form living mats, clinging to the sea floor. For around 3 billion years, this has essentially been the extent of life on Earth. It's a planet dramatically different from the world we live in today.
Large, complex organisms that we have today, like plants and animals, wouldn't have existed.
800 million years ago, the world would have looked pretty much alien for us today.
If you were transported to the planet back then, you might not even think anything was living there.
When in fact, Earth was teeming with life, just microbial life.
As distant as this ancient world may seem, we are connected to it. Because the origins of animal life today can be traced back to those shallow coastal waters 800 million years ago. Amongst the bacteria are giant cells that tower over the living mats. They are called eukaryotes and are the ancestors of all plants and animals living today, including us. Slowly evolving for over 1 billion years, larger and more complex than bacteria. They require more energy and nutrients from their surroundings. They are sustained by bacteria in the water and minerals washed in from the slowly eroding land. It's enough for them to survive, but probably too limited for them to get any more complex.
All life on Earth is essentially made up of 2 types of cell, which we call prokaryotes and eukaryotes.
Prokaryotes are very simple, microscopic life and include many bacteria, with a loop of genetic material floating in the cell.
A eukaryotic cell differs from a prokaryotic cell in that it contains all of its DNA inside of a central package that we call a nucleus.
And these cells have a lot of other structures inside that we call organelles, and that have special different functions inside the cell.
This is why we consider them more complex. It's a radical change from before.
When they first appeared, they would have looked very simple.
But over time, developed into more familiar forms.
This is tiny fossil from North China, and it looked very much like modern seaweed, but it's just small, orders of magnitude smaller than modern seaweed.
But for life to gain a foothold and further diversify, the Earth itself needed to change. In fact, the story of life is the story of our planet's changing geology.
Life and rocks have co-evolved over billions of years. They're totally interconnected, interdependent on each other.
Geology and biology are entwined together in the formation of the Earth.
When you think about geological timescales, it's actually quite easy to think about the really long-term, complex evolutions that can happen.
To understand these sweeps of time, you have to learn to think like a rock. Things happen very slowly if you're a rock.
And on Rodinia, an epic geological process will change life forever. It's on vast geologic timescales that profound and lasting change becomes apparent.
So we're in Iceland, and that kind of long-term geological change is happening here right now. It's really amazing knowing that I am standing on a place where 2 tectonic plates are pulling apart.
Tectonic plates are giant slabs of rock that lie beneath land and ocean and are constantly on the move.
That process happens about 1 to 2 inches a year. That's about the same speed that your fingernails grow.
This might not seem fast, but over time, movement like this has formed entire mountain ranges and torn continents apart.
The rocks beneath my feet are being pulled apart along the mid-Atlantic ridge, which runs this way and this way for thousands of miles and has been opening for almost 200 million years.
These tectonic forces from deep within the Earth have been creating and then destroying Earth's most prominent features for billions of years. And around 800 million years ago, they began to divide Rodinia. Deep underground, over millions of years, swirling currents of heat cause tectonic plates to shift. Great rifts gape open across the landscape. This vast continent is slowly being ripped apart. Over millions of years, it creates deep valleys and new seas, reshaping the continent. Minerals and nutrients wash from the land into the seas. Making the world around these eukaryotes a much more enriched place to live. This influx of resources radically increases their number and variety. And they are not alone. The whole ecosystem becomes filled with new and more complex life. The world is beginning to see more interconnectedness between organisms, driven by Earth's dynamic geology. We can find some incredible evidence for this in the fossil record.
Fossils themselves are really small and they're hard to find. It's like trying to put together a puzzle when you only have half the pieces in the box. So this rock here, it's got the gray part and the dark part. And both of these contain microscopic fossils. They're structures that were made by early eukaryotes. And maybe 40 of them would fit in the period at an end of a sentence.
What these tiny fossil cells tell us is they were interacting with one another in an entirely new way.
We can see spikes, spines, and other really amazing structures made from minerals that eroded off of Rodinia. It's energetically costly to make structures like this, and so there had to be a really good reason for organisms to spend all of this time and energy making them.
One idea to explain this evolutionary development suggests that early eukaryotes were facing a deadly new threat.
So we think these organisms made these structures as defensive weapons to protect themselves from being eaten. They're some of the first evidence of predation in the fossil record.
So what was eating them?
I think the most exciting clues are that we see holes that are similar to bite marks, but in this case, they're microscopic. They're tinier than a thousandth of a millimeter in size.
More evidence is found in fossils from the Grand Canyon.
So the fossil remains in this rock are little casings of organisms that look remarkably like a modern group of organisms that live today called testate amoebae. that are voracious predators.
They make holes in cells to suck out their prey, suggesting that something similar may have been eating ancient eukaryotes. If true, this would have changed everything.
Predation, just like environmental pressures, can push life to experiment and try new things.
There's a good chance that the seas around Rodinia may have been teeming with more diverse life than ever before.
And this life is slowly becoming more recognizable. But it's about to come under immense pressure.
Although the supercontinent breakup could have helped fuel eukaryotic life, it also set into motion a series of events that could have led to catastrophe for them.
And that catastrophe begins with fire. On Rodinia, geological change accelerates rapidly. Superheated magma bursts through the surface as rifting thins Earth's crust in multiple places. Molten rock swamps over 800,000 square miles of the continent's surface. One of the largest outpourings in Earth's history. As this lava cools, it becomes a dark rock called basalt, creating a vast black stain across the heart of the continent, which will have dire consequences.
Basalt is incredibly important at impacting the atmosphere of the planet.
Basalt breaks down more readily than other rocks, like granite, in a process called silicate weathering.
So when rain mixes with carbon dioxide in the atmosphere, it forms this weak acid that falls onto our surface, weathers these rocks, weathers these silicates, and creates these compounds that wash into the oceans and eventually form carbonates, so trapping carbon dioxide in the form of rocks on the seafloor.
This can control our climate on a geological timescale because it can affect the amount of carbon dioxide that can be drawn down from the atmosphere.
So when millions of tons of this rock poured out over the surface of Earth in the heart of Rodinia, it could have had a profound effect on Earth's climate.
The amount of basalt created only tells part of the story. Where it formed also plays a role.
We think that it formed around the tropics, and this means they would have been subject to huge amounts of rainfall.
So the combination of large amounts of basalt being exposed at the Earth's surface and heavy, intense rainfall meant that a large amount of carbon dioxide was drawn out of the atmosphere.
This cools the Earth.
And this is because carbon dioxide is a greenhouse gas. It traps heat trying to escape from Earth, kind of like a warm blanket on a winter's day. So you make that blanket thinner, the Earth has to get colder as a result.
Falling levels of carbon dioxide cause temperatures to plummet over millions of years. Eventually, ice forms. At first, it's confined to the poles, but it spreads. And for life on the planet, that's a potentially deadly challenge. Today, in certain places on Earth, you can vividly see the impacts that ice and falling temperatures have on ecosystems.
In the valleys surrounding high mountains in a mountain range, you might expect to see a lot of different types of life. It's a very lush and hospitable environment.
But as you go up the mountainside and temperatures get a little cooler, we start to see fewer and fewer kinds of life flourishing.
Cold and ice can destroy cells and slow down chemical reactions, impacting life.
It's likely that 717 million years ago, as the snowball Earth glaciation began, microscopic webs of life were also threatened.
On ancient Earth, the cold advances on early life. Sheets of sea ice thicken year by year as they creep towards the shores of Rodinia from the North and South Poles. And on land, huge ice caps expand down from the mountains. The places life can hold on are rapidly shrinking. As the ice tightens its grip across the planet. The big question for scientists is, why did this cooling trend turn into a runaway deep freeze?
It's not like there's never been supercontinent breakup or vast outpourings of basalt before, so what was so different this time?
It's really difficult to find out exactly what happened millions of years ago because all we have left is this incomplete rock record. And translating that into its climate impacts is a very complicated process.
It could have been that because Rodinia was breaking up around the equator, that caused a lot more weathering than other supercontinent breakups in the past.
One theory suggests new complex life may have changed ocean chemistry, which drew down carbon dioxide, trapping it. Another involves volcanic gases.
These large volcanic eruptions put a lot of sulfur dioxide, which turns into sulfuric acid, into the atmosphere, which reflects sunlight back to space,
cooling the Earth.
Once this cooling began, it would have likely been incredibly difficult to stop.
The ice is bearing down, but a web of life can still thrive at lower latitudes. As the white expanse spreads, it reflects more of the sun's energy back into space, driving down temperatures and expanding the reach of the ice, until it becomes a runaway process. This is known as the ice albedo feedback effect.
Once you cover a little patch of Earth with ice, the albedo of the planet has risen, which means it reflects more light to outer space and cools down, causing more water to freeze into ice, which reflects yet more light into space, cooling the planet on and on and on.
Driving a continuous loop of self-reinforcing change that remakes the surface of the planet. Sea ice surges over the oceans, reaching a crushing half-mile thick in places. And near the equator, ice closes in. Creating a frozen planet. We suspect Earth became a snowball because we know how far the ice reached, thanks to clues that were left behind.
So today, if you look underneath glaciers, you can see rocks that are trapped at the bottom of the ice. And then as it advances out to sea, it will carry these rocks along with it. And then as it melts, these big rocks at the bottom will drop into the deep ocean.
Scientists call these drop stones because once they drop to the bottom of the ocean, they become embedded in the sea floor and look different from the surrounding layers. Over millions of years, that ocean floor turns to rock and can be exposed as dry land.
This rock, funnily enough, is from the desert in Namibia, but you can see there's this big other rock embedded in this brown mass. The only thing that could have dropped this stone into the ocean would have been ice.
These drop stones from the snowball Earth period have been documented literally around the globe, and that's how we know that snowball Earth was an entire global event.
There's still a lot of debate, however, on what exactly the snowball Earth might have looked like.
We rely on our knowledge of the geological record as well as computer models to tell us what snowball Earth would have been like.
One of the ideas is something we call a hard snowball. A complete entombment of the planet in ice, with not even any communication between the sea and the atmosphere.
Another theory is called slush ball, or water belt Earth.
So slush ball Earth would have kind of looked something halfway between our Earth today and a full global snowball. There would have been ice extending down, but probably some open water still around the equator.
Other models suggest that while the seas would have been mainly covered by ice, on land there would have been things like dry valleys and exposed mountains, like Antarctica today.
Whatever the scenario, this frozen world produced incredibly harsh conditions.
We're talking about temperatures near or below freezing, even at the equator.
Climate models predict that the ice covering the oceans would have been several hundred feet to half a mile thick.
This would have had a huge impact on life. As the ice chokes our planet, it is a disaster for the majority of living things. Under ice, the ocean is mostly cut off from the atmosphere. Darkness closes in, and the flow of nutrients from the land slows to a trickle. Under this pressure, ecosystems begin to fall apart. Imprisoned by the ice, the predecessors of all animal life falter. And many die. It's easy to imagine how this could have ended all complex life on Earth.
We know that life must have survived through snowball Earth because we still have a lot of life in the Earth today. We had life before and after, so somehow it must have survived.
But it's hard to prove where, as all the ice from back then is melted.
To understand how life survived in ice in the past, then we look to how life survives in ice today. And there is one habitat that snowball Earth scientists are particularly interested in, so we're going to see if we can try and find that today.
There's more to this frigid landscape than meets the eye.
What I found here is a hole in the glacier surface. We refer to this as a cryoconite hole. Sediment lands on the glacier surface, swept in by water and by wind. Then the radiation from the sun warms it and it melts the underlying ice. So it melts almost vertically down to make this pocket that we see here with meltwater at the bottom and open at the top.
Look hard enough in the right places, and you'll find these on glacial surfaces everywhere.
The cryoconite holes are perfect for microorganisms because they have access to the sun and they have access to meltwater.
That makes these holes refuges for a variety of life.
I'm going to try and sample this cryoconite hole. I'm seeing some bits are a little bit green, so they might be bits of photosynthetic microorganisms, or they might be bits of plants.
Other samples have revealed even more life.
A huge range of organisms, from fungi to microanimals. This captures the diversity of the organisms living in cryoconite holes, not just in species, but in size and shape and function. It's surprising and it's quite magnificent that these quite empty-looking spots can have this much diversity.
Even when life like this is subjected to harsh snowball Earth conditions, it survives.
For us as humans, snowball Earth will always seem like a harsh, almost impossible planet to live on. However, when we look at the depths of Antarctica and the middle of ice sheets in the Arctic, there is life wherever you look for it.
And it's not just cryoconites. There's various different places eukaryotic life may have survived on snowball Earth.
It could have been in little glacial ponds or lakes, hot springs, which surely would have been around then as they are today.
Some may have survived deep underground in subterranean caves where there's water and temperatures are higher. And then, of course, the oceans.
But this is no easy life.
For life to flourish again, we would need some kind of drastic change for life to escape this icy prison.
Ironically, this change would be driven by the same powerful tectonic process thought to have triggered snowball Earth in the first place. A process that had never stopped. Deep below Earth's surface, the fire still burns. The ice can't stop volcanoes from punching through the planet's frozen shell.
Even in the depths of the snowball Earth period, volcanism would never stop completely because there would still be Earth's internal heat driving it.
But it is not heat from the lava that impacts Earth's climate.
Lava is not what melts the snowball. It's actually an invisible force, which is the carbon dioxide being produced by volcanoes and building up in the atmosphere.
This would have served to trap heat against the Earth, causing a rise in global temperatures.
Before the snowball Earth period, carbon dioxide was removed from the atmosphere by reacting with seawater or with rocks on land via silicate weathering.
But if you cover the entire planet in ice, as was the case during snowball Earth, this is effectively shut off.
The ice layer would stop the weathering process that had been pulling carbon dioxide from the atmosphere.
And so the carbon dioxide builds up into the atmosphere until it gets warm enough to melt the ice.
As each eruption tears through the icebound plains, it releases a mix of volcanic gases, including carbon dioxide, each time adding to the atmosphere, leading to tiny increases in global temperature. As concentrations rise and build over millions of years, the gas traps ever more heat. The frozen planet begins to thaw. How long it took is still debated.
Almost everybody agrees that in geological terms, the melting, the deglaciation of snowball Earth was really fast. Where the disputes are is whether fast means a matter of hundreds of years or maybe up to 1 million years.
It is incredible to imagine that a global glaciation could have been undone in just a couple thousands of years. This is a geologically instantaneous amount of time.
The rapid 1,000-year melting speed is a contentious theory, but there are geological clues left that support it.
We don't know precisely what happened millions of years ago because we weren't there. But one theory is that by looking at these types of rocks, called cap carbonates, we can understand how snowball Earth melted.
These are found in vast quantities.
This was actually found in a rock sequence that was 72 feet thick, so that's a whole cliffside. One idea is that they represent the products of the intense chemical weathering that happened at the end of snowball Earth as the snowball was melting.
But this rock can also suggest how fast it happened.
If the melt had been slow, impurities would have had time to accumulate in here, and that's not what we see. There's no impurities within it. This tells us that the melting was actually very rapid.
Further evidence that this could have happened in around 1,000 years. $635 million years ago, as the planet warms, the melting of gigantic glaciers drives intense evaporation of water into the atmosphere.
Water vapor is a strong greenhouse gas, so this would have kind of acted like an accelerator pedal on the whole process.
Once the thawing begins and the ice caps start to retreat, the planet becomes darker, enabling it to absorb more energy from the sun.
As the dark oceans and continents absorb more heat from the sun, this would have helped warm the planet and decrease the amount of ice left on it.
This can be considered the exact reverse process of how the snowball was formed.
But this is not a tranquil time.
When the snowball Earth ended, it ended in a catastrophic way.
What starts as a trickle becomes a torrent. And the melt becomes unstoppable. A runaway event that releases a deluge of meltwater on an almost unimaginable scale.
You can imagine these huge waterfalls coming off the edge of glaciers.
You would have almost certainly had these really massive tropical storms, unlike anything that we see today. We call them hypercanes.
There must have been acid rain coming down from the skies above, just completely obliterating the surface of the Earth.
At the peak of the melt, sea levels rise over 6 feet every decade, swallowing great chunks of coastline. After a total of over 50 million years in the deep freeze, the world beneath the ice finally emerges. Its warm shores a stark contrast. Perhaps over 120 degrees Fahrenheit at the equator.
If you were transported back, the oceans would have been very tropical.
That change from freeze to fry is a big challenge to all kinds of life.
Eukaryotes and all life on Earth, of course, would have evolved to the warming temperatures, but evolution is slow and doesn't happen overnight.
Many would have died, and those that survived would remain reliant on nutrient streams from the land. This is a changed world. The land utterly transformed by the incredible power of glaciers. A force that can still be seen today.
Well, I'm lucky enough to be standing at the foot of a glacier, and this big face here next to me, it's really dark, really black, but it's not rock, it's actually ice. And although it looks pretty stable and static now, it's actually moving towards me at 3 feet per day. And it's a really kind of eerie place to be standing. If we look up into the mountains, we can see that this glacier has carved its way down into this deep valley right to where I'm standing. This has broken up all of this material around us, and these boulders, and then this really fine clay-like material as well. But imagine this happening during snowball Earth across the whole planet.
It's thought that the glaciers back then were just as scouring as today's.
These glaciers were able to remove about 2 miles of rock from below them. That's about twice the depth of the Grand Canyon. So the power of these glaciers was enough to remove vast swathes of the rock record, leaving behind gaps.
Many scientists believe that this could explain a geologic mystery known as the Great Unconformity.
So this rock is about 520 million years old, but it sits just above this 3 billion year old granite. So the amount of time missing is about 2.5 billion years. And we think that the rocks may have been partly eroded away by glaciers during the snowball Earth period.
Another theory is this gap may be due to the movement of tectonic plates.
But if it's true that glacial erosion is responsible, we're talking about more than a vertical mile of erosion on average globally. That's 1 billion tons.
This incredible amount of ground-up rock is deposited in the world's rivers and oceans, helping single-celled algae and bacteria to flourish, growing in massive blooms, likely visible from space. And these may have impacted the entire ocean's systems. The oxygen levels in the water greatly increase, generated by high levels of photosynthesis. In the aftermath of the Great Thaw, conditions seem possible for eukaryotic life to take another leap forward.
The oceans would have been a really great place for life, with sunlight, oxygen, warmth, and nutrients.
And the melting of the ice would have created more shallow marine habitats to expand into.
It's a time when life really has a lot of opportunities to experiment and diversify.
Once more stable and productive interaction started to happen between the Earth and life that existed on it, it didn't actually take that long for much more complex life forms to evolve.
This is a major turning point, unlike anything that came before. Finally, individual organisms are becoming complex and big enough that we could see them with our own eyes.
Some scientists think that the increase in the size of eukaryotic life has to do with the availability of oxygen.
The increased availability of oxygen may have allowed organisms to access a greater amount of energy than perhaps they were previously doing.
It's also possible that phosphorus played a key role. Photosynthesis requires phosphorus, and that forms the basis of the food chain. This could have fueled a very productive ecosystem.
And it might not be oxygen or phosphorus or any of the other theories we have, and it may just be they needed the time and the space to evolve.
In shallow coastal waters, across the planet, life blossoms. This myriad of strange forms may all look like plants, but some are animals, grazers, predators, and prey. Descendants of those first tiny pioneers, but more complex. Now, collections of these cells work together, finally broken free of the microscopic world. All living within and supported by a web of life, just as intricate and productive as any on Earth today. These first truly complex living creatures are ediacaran organisms.
Life has been on this incredible journey. We've gone from these tiny, microscopic little fossils that we can only see with microscopes, all the way to these large, complex organisms which show signs of having animal features.
This fossil, Elingia, was found in South China, about 550 million years old. What you're looking at is a trail made by this animal, perhaps in the last day of its life, and then it died, and then the animal and the trail it made were preserved together.
Striking proof these animals moved and made choices over where to go. But these creatures are so odd-looking, they are hard to study and classify.
So this is something called Dickinsonia. It is probably an animal, but scientists are still debating what kind of animal exactly it is.
Trying to understand how they interacted with each other is tricky.
Gonna press red button.
But thanks to advanced laser technology, scientists can now learn more about them than ever before.
So by laser scanning these fossils, we've got a three-dimensional surface covered in the fossils. And what this means is you have essentially a snapshot of ediacaran life captured on the rock surfaces. To date, we have over 20,000 fossils that we've laser scanned. And using different sorts of statistics and mathematical approaches, we can then work out what they were doing and how they're interacting with each other.
Looking at the whole ecosystem is helping scientists gain precious knowledge about these animals and how they interacted with each other.
It doesn't seem that we have any of the creatures from the Ediacaran period still alive today, except for sponges.
The geologically short time that the Ediacaran fauna were around on our planet indicates that after snowball Earth, the evolution of complex life occurred at a rate never seen before.
Complexity increased and ecosystems diversified, leading to the ancestors of large animals and plants in our world today.
Great climate and a geological change took eukaryotic life to the edge.
But it seems that eukaryotic life always found a way to persist.
Eukaryotic life has survived events that scientists previously thought were unsurvivable.
Re-emerging, diversifying, and exploring every possible niche that the world has to offer.
Our Earth finally became the stage that ushered in a new age. One of complex life that would eventually reach the scale, beauty, and complexity that we see today.
Be more PBS.